Hi everyone who is watching us today, live or recorded, doesn't matter, from any part of the world. I'm glad that you are here today with us again, and we're going to show you episode 4 from our training video series. And this episode is going to continue subject of signal propagation, and there is a phenomena which is going to be explored today, and you can see this phenomena visually in how does this pencil look like. So you can guess what is it, why it looks broken, and what physical phenomena allows us to see it like this in this condition. And I guess that you already know the answer, and this phenomenon is called refraction. In this case it is a light refraction, but it can be any radio wave, electromagnetic wave refraction. Of course we will be talking about any type of electromagnetic wave, but we will refer to light as well as a very visual example of what is happening here. But before we begin, I would like to get back to the previous lecture and answer a question which was asked related to Huygens principle. The question was related to the fact that the secondary wavelets doesn't propagate backwards, so they only propagate in the forward direction, and thus forming the wavefront and moving the wavefront further and further from the source. So the question was, why don't they go backwards? Why don't they oscillate in the backward direction? And actually the answer to this question hasn't been answered by Huygens himself back in the days, and also Fresnel didn't have quite a good explanation of this. He just made an assumption. Another scientist who amended Huygens' Fresnel principle was Gustav Kirchhoff, and he was the first who derived an exact expression of what is going on there. So he corrected Huygens' principle and he added some additional conditions to this principle. And he mathematically proved that it can be correct, and we don't have any backward oscillations. So this is what we call now the obliquity factor or inclination factor. And it says that the amplitude of the wavelet is dependent on the direction, on the angular deviation from the normal to the wavefront. So in the direction of the wavefront propagation, we have the maximum amplitude of this wavelet oscillation of the secondary sources. So they oscillate in the forward direction with the maximum amplitude. And if we decline from this normal position to the wavefront, from this perpendicular, the amplitude diminishes, and it diminishes to 0 when we go to 180 degrees backwards. So that is why this wave doesn't propagate backwards. And also Kirchhoff presented the mathematical explanation of this, but of course we're not going to talk about it today. So this was just an example of how we can explain and how we can amend this principle. Of course, this principle is something artificial, and this is just for our basic understanding of what is going on there. And actually the things are more complicated than this. This is just a basic visual concept of how we can present the wave propagation in space. So if we accept this model, then we also have to accept some conditions. And one of the conditions is this amplitude deviation from the maximum when the angle deviates from the 0-degree angle according to the wavefront propagation direction. So that's the answer. And now I'm going to show you the answers to the previous quiz as well. And actually, most of the answers have been answered, most of the questions have been answered correctly. So there is nothing really to discuss a lot about all these questions. However, one of the questions brought some controversy, and I'm talking about the question number 3, because there was a trick for you, and also there was a discussion with one of my colleagues. He came to me 2 days ago and he said me that this first example of diffraction is not actually a diffraction, but let us start with the third one. So the third one was a trick. I didn't refer to this effect, but some of you answered correctly that this is also can be considered as a diffraction example. Why is it so? Because the surface of the CD or compact disc has a pits and lens which contains all this binary information recorded there. And these pits and lens act as the slits in the diffraction grating. And the diffraction grating is what makes it possible to visualize the diffraction effect with its minima and maxima patterns. For example, famous Young experiment, double slit experiment, proved this wave nature of light. And this diffraction grating actually is something made on purpose for proving the wave nature of light, for proving the diffraction of light. But here in this CD, we also have something similar to the diffraction grating, which works as a diffraction grating actually. And what happens there? The light, first of all, gets diffracted and reflected from the surface of CD. And the diffraction takes place as well, also depending on the wavelength of the component of light. We have something we can call dispersion, where there are different angles of the diffraction for different components of light, for different colors. And that is why we separate this white light, which bounces off the surface of CD, to different colors, which is included in the simple light beam. So we see this rainbow color of the CD because of dispersion which takes place there. So there are multiple effects, but all of them are related, have the same nature, and related to wave propagation. So that was the hook. As for the second is clear. This is an example of a water wave going through the opening and forming the secondary front, which propagates according to Huygens principle. It's clear. And what about the first one? So my colleague mentioned that this is not a diffraction example actually, yeah? And I started to search internet and found some controversy about this subject. So in some examples, this was mentioned as an example of diffraction. However, this can also be described as a scattering of light. So the argument of my colleague was that the opening of the door is not of the same dimension as the wavelength of light. So we cannot see the diffraction going on there, right? We cannot produce the diffraction effect which we could produce if the opening was small enough to cause this diffraction. For example, the diffraction grating, where we see this pattern of minima and maxima. Yeah, I agree with that. The dimensions of the open door, half open door, is much larger than the dimensions of a wavelength of light. And probably what we see here can be called scattering. But the thing is that the diffraction and scattering are very often used interchangeably. And in the literature, it is very difficult to find a clear distinction between the two. It is the same as we spoke last time about the interference and diffraction. It's about the same property, but maybe it shows itself differently in different conditions. Here it is the same. The diffraction and the scattering are both properties of light propagation. And sometimes, and they share their common nature in some sense. I will explain it a little bit more in detail because it will be related also with the refraction, which is another phenomenon related to these two, to the scattering and to the diffraction. So all of these are closely related between each other. And sometimes we cannot even tell the difference. Of course, we can call this scattering this time, right? The same applies to this example of the sunbeams going from the cloud, from the sound abstracted by the cloud. Okay, we can call this diffraction in the particles of air as well, and the diffraction, not the diffraction, sorry, the scattering of the light, and forming of these rays with distinct regions of brighter and darker pattern. But sometimes the diffraction takes place here as well, and it's called iridescence of the clouds, when the sun is obstructed by the cloud, but some tiny particles of the atmosphere causes light to diffract, and then we see this light. We see the light coming out from the clouds, and this can be called refraction. So in some cases, this is just a case of classical diffraction. In this case, is called scattering. But the nature of these two phenomena are very similar and very closely related. Some comments from Christophs about this topic. I meant not scattering in a pure sense in volume, but scattered reflection from the door surface and the wall. However, I value greatly these examples. It makes us all think about the processes around us. Okay, thank you for explanation, Christophs. Actually, this controversy about this question made me make a little research about the diffraction terminology as it is. And here are some examples of diffraction definitions. So in Britannica, diffraction is defined as the spreading of waves around obstacles. Okay, clear enough. In Wikipedia, it is described as diffraction is defined as the interference or bending of waves around the corners of an obstacle or through an aperture into the region of geometrical shadow of an obstacle aperture. Okay, this definition includes interference, as we learned last time. So we know that interference is what is going on there as well, what underlies the diffraction process. And an aperture here is also mentioned, and probably this takes into account this diffraction grating and this classical diffraction pattern effect. However, another article which I found in a scientific journal of quantitative spectroscopy and radiative transfer states that diffraction is the spreading of waves of any kind. So it doesn't even mention the obstacles or bending around the obstacles. It just generalizes this terminology as the spreading of waves. So it is in a broader term. That's interesting because this article went that far that it made an attempt to reevaluate the diffraction the scattering and the shadow itself. So it took as an example a light wave, and it proved based on different theorems, which we will be talking about later, and Huygens principle, proved it that actually diffraction is a subcase of scattering, and the shadow, the forming of the shadow, which was the most interesting part for me, is a subcase of scattering. And in that sense, this article stated that actually there is no way to block the light wave, and that what we see is the scattering. What we see is the obstacle itself emitting the extinguishing wave and producing the destructive interference with the direct wave. That is why this wave is cancelled behind the object, and that is why we don't see any light going through the object. So this article assumed that the shadow forms not because of the obstacle blocking the source of light, right? But because of the property of this obstacle itself, according to this principle of extinguishing wave. So there is a wave generated by the electrons of the matter of an obstacle itself, which produces this extinguishing wave, which cancels the direct wave. And this was very interesting for me to consider it from that point of view. We can argue about this. This is a sort of metaphysical question, maybe, or a matter of interpretation, but it is very interesting to think about this. Well, now we're going to get to our main topic today, to the refraction. Let's start with the beginning. Let us start with a question for you, our dear viewers. Can the radio wave velocity exceed the speed of light, which you can see on your screen in meters per second? So what do you think? Is it too obvious for you? Even if the answer is too obvious, you can write it down in the comments, any of you, and we will discuss later. So what do you think? Are there any conditions maybe, or the answer is yes, just yes, simple, or the answer is simple no, even without any explanations? What is your guess? Everyone is shy? No. Okay, the answer no seems correct to us intuitively, right? Because if it would exceed the speed of light, it would contradict the physics as we know it. All laws of the physics could be violated by this assumption. So the answer no is no, but it's not that simple as it can seem from the first sight, because if we are talking about the velocity, which velocity we are talking about? There are two different kind of wave propagation velocities. No? Yes, no, with question mark. So when I started explaining, somebody from you started doubting about this. Okay, that's good. That means we are thinking about the concept. So there are two types of velocity. The first one is phase velocity, and the second one is group velocity or signal velocity. So, okay, this will be later. If we're talking about the phase velocity, what is it? The phase velocity is the speed of wave of phase propagation of the wave. So, this is the velocity of the phase propagation, or we can say the crest of the waveform, which propagates in the space. That's one thing. The other thing is the group velocity, and the group velocity is the velocity of the wave envelope propagation. So I mean overall wave envelope. If we have, let's say, a modulated signal with a carrier, So this envelope is going to propagate with the group velocity. And the same term is also called sometimes signal velocity. Why? Because we because we send some piece of information with this. And it turns out that the phase velocity under certain conditions could exceed the speed of light in vacuum. That's very mind-blowing, right? But that it doesn't contradict any rules of physics, any laws of physics, and it doesn't make it supernatural because we don't transfer any information with this phase. This is the speed of the phase of the signal, not the actual signal, not the group velocity. The group velocity or signal velocity cannot exceed the speed of light in vacuum. And so when we are speaking about the phase velocity which exceeds it, we're speaking not about some energy transfer or some information transfer, but some more mathematical concept, right? So not literal concept, not physical, materialistic. So we can speak about the phase velocity which exceeds actually the speed of light. And let us take a look at the next formula which defines the refractive index. And the refractive index, which is the parameter which defines with which velocity does the wave propagate in the certain medium. So the refractive index is dependent on the medium, and it differs. For example, for the air, for the glass, for the water, each of these materials have its own refractive index. And the refractive index can be defined as the relation between the speed of light in vacuum and the phase velocity. It also can be defined as the square root of the dielectric constant multiplied by the magnetic constant, or relative permittivity multiplied by relative permeability. And these two parameters also describe the medium where the light propagates, or any electromagnetic wave propagates, right? But we'll get to this later. And so far, I'll have to take into account that here in this refractive index definition, this is the phase velocity which is taken into account. So there could be different cases. There is a special case when n, or refractive index, is less than 1. We will talk about it a bit later. And it refers to the so-called sky wave propagation in Earth ionosphere. And in this case, it could be that the phase velocity is greater than the speed of light in vacuum. I will explain it a bit later. The typical case is when n is greater than 1. So this covers most of the materials. We're talking about light and the materials which are transparent for light. And we're talking about the electromagnetic waves of any frequency. And we refer to any materials which are transparent to these frequencies. Now, the refractive index the refractive index is not only how we can evaluate the phase velocity of wave propagation, but also something that we can use to describe the refraction process. So this is the classical example of refraction. What is going on there? The light beam falls into the glass and it gets through the three media. It gets initially from the air to the glass, then from the glass to the water, and then it reflects from the pencil and gets back the same way to hit our eye and to allow us to see the pencil inside the glass. So why it looks broken? Because of the refraction, because it gets light to change its trajectory to get through all these three media. And it matters whether some part of the pencil is visible from underneath the water or just in the glass where there is no water. So because of different properties of different media, the refractive indices are different for the air, for the glass, and for the water. And this is what defines the refraction. According to the Snells Law, which binds together the angle of incidence and the angle of refraction when the light or any other electromagnetic wave travels from one medium to another medium. So when this happens, we can see the change in the angle of incidence and towards the interface, according to the normal to the interface, right? So the speed of propagation changes, or such called phase velocity changes, because of different media and different refractive indices. And also the angle of incidence and of refraction changes. It's different. That is why the trajectory of the wave changes as well. And that is why we can see this broken pencil inside the glass. That is why the radio wave is not going a straight line in atmosphere, but we will get to this later. And here are so far some refractive indices of some basic materials which are transparent for light and which allows us to evaluate how the light propagates through them. So for the air, it is very close to the vacuum case. It's a bit over 1. So the air is very similar to vacuum in that sense. However, the water exceeds it by 1/3. So it's for the water, there is a typical case when the refractive index is larger than for the vacuum, and for the diamond it's much larger. So the refraction will be even more evident in the diamond than in the water or than in the air. Okay, so another parameter which can be derived from this is the so-called velocity factor, which is expressed in percents. It is abbreviated as VF, and this is the opposite to the refractive index. So we divide the phase velocity of propagation with the light of speed in vacuum, and we get this inverse relation which shows us how fast the signal travels in any medium, comparing to the light wave in vacuum. And sometimes the optical fibers, the light propagation in optical fibers, or electrical wave propagation in some other transmission lines can be described by this velocity factor in percentage. So for the engineers, this is more practical to use this notion, and it can be used for some transmission lines characteristics. Okay, and now let us take a look at the scattering. We'll get back to the scattering to explain the effect of the scattering and of why does it matter to even talk about scattering in that sense. So let's talk about scattering a little bit. I'll show you an example. So what is scattering? Scattering is the change in trajectory when the light or any other electromagnetic wave propagates through the atmosphere or through any transparent object, right? But what is going on there on the microscopic level? Let's find out. Here's some imaginary particle, and here's our wave, the incident wave. Well, it can be light wave, it can be electromagnetic wave, doesn't matter. The thing is that when it hits the particle, it's getting scattered. What does it mean, scattered? It changes its trajectory. It's going on here in this direction or there in this direction, so it can go anywhere actually. By the way, the scattering is an effect which allows us to understand why the sky is blue, because the blue part of the spectrum of light is scattered more than the others when going through the atmosphere. But back to the scattering. So what is going on there on the microscopic level? The following process. This incident electromagnetic wave makes the electrons inside the material or inside this particle to produce its own wave. So they also produce some other wave which propagates. This can be called the secondary wave. So the original light wave and the light wave which is emitted by these moving electrons or in the particles or in the material. So this wave excites the electrons inside the particles or inside the material. And excited electrons, while moving, create its own electromagnetic wave, which propagates further. And the thing here is what happens when these two waves, the original one and the emitted one by the particle itself or by the material itself, when they interfere with each other. And it's very interesting to consider interference in this case as well. So we can see that interference is included in the scattering effect as well. So what happens there? We have different options here actually. So the combined wave or wave packet can change speed, but how? The first option is that the wave which is emitted by this electron of the particles is 90 degrees out of phase. So let's write it down here. So the first case, we have a phase difference of 90 degrees between the direct light, the incident light wave or electromagnetic wave, and between this emitted wave after it gets scattered. So if we have a 90 degrees phase shift, then it slows down the incident wave. The phase velocity changes. It slows down actually. And this results in a refractive index which is greater than 1. This is a normal case. This is the classical case for most of which works for the most of the materials. It's very interesting, right? The phase velocity of the combined wave, of the wave packet, let's say, gets lower. So we slow down this wave propagation. Then the second case, if the phase shift is 270 degrees, then the effect is opposite. Then this phase velocity increases and the wave travels faster than that. In that case, we are talking about refractive index which is less than 1. And this is a special case which I mentioned related to the ionosphere. So the electromagnetic wave propagation in ionosphere, which can be considered an example of plasma. So there are free particles, free charged particles, electrons in the ionosphere, which produce this effect of fastening the initial electromagnetic wave. That is why the phase shift, the phase velocity is greater than the speed of light in vacuum, and the refractive index of this can be smaller than 1. And this is what we called as sky waves or sky wave propagation. And sky waves sometimes are used in radio communications as well. Okay, this was the second case, which is not very common. however, have also the third case, when the phase shift is 180 degrees. In that case, we're talking about the destructive interference between the incident wave and the emitted wave. So they cancel each other, and the result is the absorption of the energy of incident wave. So in that case, we can say that the n cannot be defined. This becomes an imaginary value. But what we can say that there is no output in this case. So nothing gets through these particles. And we are talking about the absorption inside the particles or inside the material. So this is a perfect case of absorption, when the light cancels out. But it is very interesting to think about the fact that it doesn't cancel out by itself. It is cancelled by the destructive interference of the secondary emitted wave. Well, and when the phase before and phase after are the same, let's say 0 degrees phase shift, in that case, it amplifies the signal, and this is what can be seen in the lasers, in case of lasers. But this is a separate topic, and this is a stimulated radiation, stimulated emission in lasers. And this is another case. And there is also undefined n in this case. And the classical case is between 90 degrees and 180 degrees. So most of the time we see this phase shift in some transparent materials, and that means there is always some part of the absorption and some part of the refraction. So refraction and absorption are closely related cases, right? And diffraction fit somewhere here in between as well. So all of these phenomena share the common nature, and this nature can be explained by the wave propagation properties. Well, so how does it relate to our case? And why the refraction takes place? Why do we see this trajectory shift? Why do we see this theta angle change according to Snell's law? Why does it happen? Here's a short example of this. Let's say that we have some interface between two media here. And we have, again, let's take an example of a light beam. We have a light beam which is incident on this interface. So it travels like this, gets to the interface, some part maybe is reflected, some part is going through the material. So this will be air and this will be glass. And this part which goes through the glass on this interface, on this border, what happens here? Well, the refractive index of the glass and refractive index of the air is what matters. And it means that we have the difference in the phase velocity here. And this part of the light wave begins traveling faster, right? So this is this case, slower. This is this case, when n, the refractive index, is larger than 1. So it slows down, while this continues traveling with the same speed. And only later on it begins slowing down here because of different refractive indices between these two media. And that makes the whole bending of the wave. That is why this refractive, this angle of incidence and angle of refraction are different. That is why this wavefront begins to travel in other direction. So it slows down a bit. This part slows down first, and only this slows down later. So we've got something like this, for example. And we can see this trajectory change because of that. This is just a simple explanation of what's going on this interface, right? And why, due to this effect, which can be explained by the scattering. Because what is going on here, this is the scattering, which is going on here through the material of glass, through these atoms of glass. And due to different properties of how this incident wave and this emitted wave behave and add to each other, of how the interference occurred there, based on this, we have this change in trajectory and change in the wavefront speed velocity, phase velocity here. Okay, let's get back to our presentation. Hi, yes, this is live. You're right. I can read your comment. This is confirmation. All right, so what we learned, that the refractive index of any material depends on two parameters, relative permittivity and relative permeability, or dielectric constant and magnetic constant. In turn, each of these constants are dependent on the material itself, related to the same parameter of the vacuum. So, relative permittivity is the permittivity of some material related to the permittivity of the vacuum. The same applies to permeability. Here are some numbers about different propagation media, and you can see that for the air, both permittivity and permeability are very close to 1. That means they are really similar to the vacuum, to the case of the vacuum. And for the water, you can see permeability is about 80 at 20 degrees Celsius, and permeability is a bit lower than 1. And for iron, we can say that permittivity is very large, infinite, let's say, and permeability is also very large, but not infinite. So that is why, while propagating through different media, light wave or the radio wave change the trajectory because of the properties of these materials, and because this scattering, which is going on together with absorption, of course. There is some part of absorption, some part of scattering, but when this scattering is taking place there inside the material, based on the properties of that material, the trajectory changes. And this leads us to the question about the air. Why do we see a phenomena when the radio wave is not traveling as a straight line? Why it bends down in the atmosphere? I hope this is a known fact for you. This leads us to a question. Is the air a homogeneous medium? What does it mean? It means whether the relative permittivity and the relative permeability of the air is constant in the all over this atmosphere. Let's say, does it change with the height, with the altitude? Does the refractive index change with the altitude? I'll give you some seconds to think about it. And here's the answer. Refractive index of the air is the function of the altitude. as the temperature, pressure, and humidity varies with altitude, our refractive index varies as well. So it's not a constant for the air. It depends on the altitude on these three parameters. And we can draw a chain like this here. We can make further several conclusions based on this. If the altitude increases, the refractive index decreases because the temperature, pressure, and humidity decreases as well with the altitude. As a result, the phase velocity of wave propagation increases. The sinus of theta, or refractive angle, increases as well, and the angle itself increases. Okay, what does it mean? Let's get back to the Huygens principle and to this traveling, expanding waveform. So each point of this waveform is the secondary wavelet producing another oscillation, another wave. But if we're talking about the wavefront as a whole, which part of the wavefront is going to travel faster and why? What do you think? This is a bit similar to the effect that we observed, just observed on the board concerning the traveling of the light wave to another medium, to the glass, for example. Yes, there we assumed as well the light wave as a wavefront, and different parts of this wavefront colliding with the interface at different times, changing speed at different times, and thus bending the wave. But in this case, there is no clear distinction between two media. There is no interface between this media. The air is not homogeneous. The refractive index changes with the height. So, but if we take as an example a radio wave, it can have very large wavefront, as we learned from the Huygens principle and from the diffraction. So the upper part of this wavefront propagates with higher speed than the lower part of this wavefront because of smaller refractive index. So the refractive index becomes less, the speed increases, and the sinus of the theta angle increases as well. That is why this wavefront travels faster than in case of the lower part of this wavefront. We can visualize it like this. And this is going to increase our refractive angle. What does it mean? That means the wave is going to bend down. So every part of the wavefront is going to bend down a little bit. This angle is going to increase because the refractive index decreases and the speed velocity, phase velocity increases, just the opposite. And this is what defines the radio wave propagation in the atmosphere. This is what makes the radio wave bend downwards towards the Earth. This is what normally happens with a normal atmosphere under normal conditions. This is how it would look like if we had vacuum between two towers. And we're speaking about radio wave propagation here, of course. So if it was in a vacuum, like communication between two satellites, for example, then it would look like this, just a straight line of propagation, because there is no any media where the scattering will take place and where this change in speed will take place and when this bending will take place, right? The same would be if this media would be homogeneous. But due to the fact that air is not homogeneous and the normal propagation in normal atmosphere, the refractive index decreases with the height, with the altitude. We have this normal behavior of the radio beam. We have this bending toward the Earth. And if we are talking about some abnormal propagation conditions, it could be if this decrease in refractive index is very steep, it is very pronounced. In that case, the radio wave is going to be bent downwards much more than we would expect, and this could impair our radio communications. This is one of the problems which we have in the microwaves. Yes, the bending of the radio waves and the fading of the energy of the losing the communication channel between 2 points because of these abnormal conditions. When the radio beam is bent downward that much that it doesn't get through the distance of the link, and it's not received even in the opposite direction by the receiver. And the opposite case, which is also under some atmospheric conditions, it could happen that the refractive index gets larger with the altitude. Then our signal is going to be bent upwards, which is not natural. And in that case, we can experience larger diffraction losses. So this case is not that often as the previous one, but it could happen in different parts of the world and for some small fraction of the annual time, and sometimes it also causes us problem for the microwave communications. And in order to describe the atmosphere and this change, this variation in the refractive index of the atmosphere, we have to introduce the new parameter, which is called radio refractivity. Not just refractivity, but radio refractivity. Thus, it would be useful for the radio engineers and for the microwave industry. And the radio refractivity is designated by the large N, by the capital N, and it is found as the refractive index -1 and multiplied by million. So it would be more convenient for us to evaluate the atmosphere, because as we learned, the refractive index of the atmosphere is very close to 1. That means that it doesn't differ from the vacuum that much. That is why we have to deal with very small fractions, which is not convenient. And to make it more convenient, we multiply it by million, and we get something that is called radio refractivity, and something that is very often used in the microwave industry and in the link planning. So the radio refractivity is expressed in so-called N units. This is some arbitrary units which have been invented for our own convenience, and the standard value for this N units at the sea level is 315 N units, which doesn't say as much, but we will see different N units and how does it apply to the abnormal propagation conditions. This radio refractivity can be expressed in a formula as well, and from this equation we can see that the radio refractivity is dependent on the pressure, on the temperature, and on the humidity or partial pressure of water vapors inside the atmosphere, which is denoted by E. And we can find this using this formula, which is mentioned in the ITU recommendations as well. So, but what matters to us is not just a simple radio refractivity parameter, but the change of radio refractivity with the altitude, right? That is what defines how the wave is going to propagate. That is what defines the trajectory of the wave, as we learned. The upper part of the wave front travels faster or slower, and thus the trajectory is going to change. it's going to bend upwards, it's going to bend downwards, etc. So we're interested more in this n as a function of h, or the function of altitude. And we can express it as a basic n, 0, and exponent of the change in the altitude. So yes, what matters for us is a change in the value over the radio wavefront, not just a radio reflectivity in some selected point. And there is another parameter for this, for describing this, and it is called refractivity gradient, or the rate of change of the refractive index with altitude. It is defined as dn to dh, or small differential of the radio refractivity towards the differential of the altitude change. And here's a very famous graph for the link planners, which gives us the statistical distribution of different refractivity gradient values around the world. So this was some statistical data recorded from different meteorological stations and accumulated together. And what we have here is the probability of certain refractivity gradient presence. So the refractivity gradient can vary from normal conditions to abnormal conditions when the refractive index increases with the height or decreases with the height. And in this range, we can define this range by looking at this graph. And the normal conditions are well described by this median, which is at 50% here. What does it mean? It means that this is the average atmospheric conditions, so the most probable conditions which are likely to occur at any part of the world for most of the time. And this refers to the refractivity gradient of minus 39. And this is selected as a standard atmosphere value for some standard cases, so we can call it normal propagation or standard propagation. Actually, the standard propagation includes the wider range than this, and it spans from 0 to minus 100. And under these conditions, we are going to observe the normal propagation conditions when the refractive index decreases with the altitude and when the electromagnetic wave is bent downwards to a certain extent. Outside of these limits, everything which is outside of these limits can be called abnormal propagations. Basically because statistically it is less probable, first of all, and secondly it causes headache for the microwave engineers, right? So it causes problems because of impairments in radio communications, and the link planners have to account for these effects and account for these abnormal propagation cases, how probable they are in the particular part of the world where we are going to build a link, and what effect they could give us if they happen. For example, they can result in the increased diffraction, so loss of signal power, or the blackout when we also lose a significant amount of power, and which causes, of course, worse sensitivity and lower signal level at the receiver, increased noise level, and less throughput for the radio link. So the first case of abnormal propagation is the super refraction, so-called super refraction. It is when the electromagnetic wave is super refracted, so it's refracted to a much more extent than it would normally under normal conditions, right? And it happens when the G, or refractive index, is less than minus 100. is more negative than minus 100. And based on our experience in the link planning, these values can reach up to minus 1000 and even more than that. So these are some enormous values and very unfavorable conditions for for radio communications, because we lose all the power of the signal. It cannot propagate to the receiver. It cannot reach the receiver because all of this energy is blocked, is bent toward the earth. It doesn't reach there, right? So only a small fraction reaches the receiver, which is not enough for stable link communication. And the super refraction is more common, abnormal propagation conditions, and it is very often met in desert regions and regions by the sea, especially the Middle East. We can see this is one of the conditions of the multipath fading, which will be covered in the next lecture. But for now, it is just important to understand that this can be considered abnormal, especially for the radio engineers, because it impairs the link performance, the radio communication performance. And another case, which is less probable but also sometimes present, is another type of abnormal propagation, is the subrefraction. And subrefraction just makes it opposite. We have the refractive index increase with the altitude, and we have the trajectory bends upwards. So this is not favorable for radio communications as well, because in this case we are going to have larger diffraction fading if there is any obstacles in between. Of course, we are going to lose some amount of our signal power as well in this case. Alright, so we have the radio refractivity and the refractivity gradient, which is interesting for us, as for the radio engineers and for the radio planners. But there is still some parameter missing for proper link planning, and this parameter is the effective Earth radius, which is designated by the small key, lowercase key. This is quite a complicated concept, but we're not going to get into the detail, right? The main point of this key factor is that it artificially makes the signal trajectory a straight line. So as we know, the signal is not propagating in a straight line in the atmosphere. It bends downwards. But when we evaluate the diffraction, when we have to take into account the first Fresnel zone clearance and whether any obstacle is going to interfere with the signal or not, with this zone or not, it becomes very difficult if you try to draw it on a paper or if you try to model it in a simulation program. It is very difficult to evaluate all these things when we're not dealing with a straight line. So the radio engineers made it straight line artificially by implementing this key factor, this effective Earth radio. But in order to maintain this relation between the signal trajectory and the Earth surface unchanged, we have to add some extra curvature of the Earth profile, right? So if we try to make the signal trajectory straight, then the curvature of our Earth profile, of course, the Earth is not flat. We all know this. We add some extra curvature to this Earth profile. And by doing this, we maintain this relation between the two unchanged. But we see a clearer picture for us. It is more convenient for us, becomes more convenient to evaluate if any Fresnel zone is obstructed, or to evaluate any reflection from the Earth surface for clearance verification, etc. And in that sense, if under different atmospheric conditions, the trajectory is different, it can be well described by the G or by the refractivity gradient, because the refractivity gradient is different, right? And by doing this, we can compare different propagation conditions and define these conditions by the radial refractivity gradient G. So in order to make our trajectory straight line, we need different key factors or different effective Earth radiuses for each of the refractive gradients, for each of the propagation conditions, for each of the trajectories. And this table on your screen gives you this relation between different refractivity gradients and key factors. And you can see that this G, which is equal to -39, which is the standard atmosphere, the most probable case recorded by statistics, it refers to the standard atmosphere, right? To the normal, ideal propagation conditions. And the Earth, the effective Earth radius in this case is 4 divided by 3, or 1.33 approximately. And this is the key factor which is chosen as a standard key factor for all link planning purposes, right? So in any professional link planning software, you will see that this is defined as the basis. And then further on you can change it based on your region, on the prospective propagation conditions, but you will start always at this point, right? With the standard atmosphere, with the most probable state of the atmosphere and most probable trajectory. When G is equal to 0, K is equal to 1, and so on. And you can see how it works if we visualize the trajectory. The trajectory of the signal is the line on the top in each case, and it is made straight in every case. You can see this. It is made straight, but it is made straight and under different propagation conditions with a different refractivity gradients. And that is why we have to take into account the effective Earth radius and to change this Earth radius. So basically, when the Earth radius is normal, like when the effective Earth radius is the same as the actual Earth radius, this is the first picture, first example. The key is 1. So we have a straight line, but the Earth radius doesn't change at all. Then it can be a minimum, it can be very high, and in this case we have to adjust the effective Earth radius to make the relation unchanged, right? And in case the key factor is infinite, the Earth radius is infinite as well. So these two lines become parallel. It means that under these conditions, which corresponds to G equal to -157, the signal is going to travel parallel to the Earth's surface all the way along. So it's not going to hit the Earth at any point. It's not going to go upper or lower. It's going to travel parallel to the Earth. And with this key factor, in theory, we can reach the further possible distance with in case of radio communications, right? So these key factors can be different, but the main purpose of this key factor is convenience for the link planners, for evaluating clearance, basically, of the Fresnel zone, first Fresnel zone, second, or etc. So this notion is quite difficult and complicated, but I try to explain it as simple as possible. And if you are involved in the link planning, that of course you are going to stumble upon this key factor very often. Even in the conversation between different link planning engineers, they are going to refer to the high key factor, low key factor, and which correspond to abnormal propagation conditions, and they are going to refer to some particular atmospheric conditions which result in signal trajectory change. So this trajectory can be bent downwards more than normal, or it can be bent upwards, and all of this produce unfavorable effects for radio communications. That is why the notion of key factor is used so much among the microwave link planners, for example. All right, so this is what concludes my lecture today. I hope this information will be practical for you if you are working in the microwave industry or radio communication industry. Please, if you don't have any questions left, then there will be questions for you in another quiz, which you are welcome to take with a link under description. And of course, we're going to discuss your answers next week, as usually on Wednesday at the same time, when we will finalize our propagation topic. And finally, for those who are asking now, where are the antennas? The series are called Propagation of Radio Signals and Antenna Basics. So next time we will conclude the propagation part, and the rest of the episodes are going to be dedicated to the antennas finally. So thank you for your attention today. Have a great day or evening.